हेलो युवराज।
जी सर।
हाँ, स्टार्ट कर दिए।
Good morning, everyone. It is my pleasure to welcome you all to the third lecture of this online certification course organized by Zakir Husain Delhi College. We are delighted to have such an enthusiastic audience joining us in this learning, and today's session promises to be both insightful and enriching. It is an honor to introduce Dr. Sushil Kumar, currently serving as an assistant professor in the Department of Engineering, Computer Engineering and NIT Kurukshetra. Prior to this, he was associated with the Department of Computer Science and Engineering at NIT Warangal. Dr. Kumar holds a BTech degree in Computer Science and Engineering from UPTU Lucknow and an MTech from Maulana Azad National Institute of Technology, Bhopal. He earned his PhD from IIT Roorkee in September 2014. His research interest lies in soft computing techniques, image processing, deep learning, machine learning, and their applications to emerging technologies. He has an impressive academic record with 25 research articles published in reputed journals and over 45 papers presented at international conferences. Dr. Kumar has also guided two PhD scholars and 12 MTech dissertations. In addition to his research contributions, Dr. Kumar has been actively involved in academic leaderships. Dr. Kumar also serves as a reviewer for several prestigious international journals and conferences, further solidifying his role as a thought leader in his field. We are truly privileged to have him with us today. On behalf of everyone present, I extend a warm welcome to Dr. Sushil Kumar. We look forward to learning from his expertise. Dr. Kumar, the virtual stage is yours now, please.
Thank you very much, sir, for such a nice introduction. So, so today we will discuss one technique in machine learning. Actually, we use principal component analysis. So here first we will discuss about the curse of dimensionality. Okay, that is curse of dimensionality. So if you know about the features and feature vectors, then it will be very easy for you to understand it actually. So I hope you know about the feature vectors and features required for machine learning. So let me discuss about the curse of dimension. I think you are getting my voice.
Yes, sir. Yes, sir.
Okay. So the curse of dimensionality is like suppose we have classes actually. So in machine learning, we have number of feature vectors are there, and we have the number of classes. Okay. Suppose I have two classes here. One is this class, and one more class I have here, omega 2. Okay, so I have two classes. So it's not limited. We are not limited for two classes actually. We can have 2, 20, 30, 100. So many classes may be there. But to understand the problem, we are taking very less class here. Okay. So when I'm writing here P actually, so this is the probability of X in W or in omega. Okay. So probability of one feature in omega class. So I have two classes here, omega 1 and omega 2. So what exactly we will do, suppose we have feature vectors of another class. So we will calculate the probability here. Okay. Suppose I have a vector y and I will calculate py omega 1. I will calculate probability omega 2, and then I will compare that it is very near to omega 1 or it is very near to omega 2. and on the basis of that we will clarify that this particular component or this particular feature is from which class. Okay, from class, we can predict it is from omega 1 or from omega 2. So there should be no confusion when I am writing omega 1. Omega 1 like a class, suppose you have number of images of cats. Okay, lot of images are there related to cats. Okay, and another class is there. Suppose you have number of images or feature vectors related to dogs. So I have two classes. So there may be so many classes, some images from cars, some images from another, like it may be from bike. So many classes may be there. Okay, and you have the feature vectors related to cars, related to bikes, related to dogs. And when you are getting a new feature from outside, that time you need to predict that particular feature or particular image, it is belongs to cats, dogs, cars, or bikes. Like that, we are working in machine learning. Same thing we are doing here. Okay, so we are calculating the probability somehow. That is different story. We are not get discuss that part here. And then we are telling that this particular image belongs to omega 1 or omega 2. So this is two class problem here. So what will happen, suppose I tell you that p omega 1 is equal to p omega 2, means somehow both are same actually probability, then it is very difficult to predict, means these two graphs will overlap with each other. Okay, so then it is very difficult to discuss that how you can calculate the correct class. Suppose, okay, this is particular area is there here. So this is the same area, actually it is overlap in two classes. Suppose you have a feature vector which is very clearly is telling you that this is from omega 1. You have feature vector that is telling you this is from omega 2 at this point. At this point. But suppose you are here at this point actually. Okay, and you are doing some calculation and the result is like that, it is telling you it may be from omega 1 or it may be from omega 2. So this is the problematic thing actually here. So how you will predict that is from omega 1 or omega 2? And second thing, suppose this overlap area will increase. Somehow this p omega 1 and p omega 2 is very near to each other. Then it will increase. This area will increase more actually here. If it will increase more, then it is very difficult to classify the problem. Okay. So what you can do, you can think like I will not take the probability. What you will take, you can calculate the variance here for one class. Okay, you can calculate for another class, but chances are there that it may also be same. You can't say that it will be always different. Okay, so this is the area where you are getting the error actually. Okay, so here if you will calculate this, suppose I have mean here, mu1, and here also I have mean, mu2. Okay, so mu, you know very well, mean actually. Mu is related to mean here. So if you have 5 values, suppose in a data stack, in your data, 1, 2, 3, 4, 5. Okay, different values are there with you. So what you will do, you will take these values and you will divide by number of 5 here, number of the variables in your data and the values. That is called mean. Okay. So you can calculate mean, you can calculate mu2. Both mean you can calculate here. So if you can guys, so this is the error here. This particular area is completely error. Okay, if you are going to increase this area somehow, okay, p omega 1 is equal to p omega 2, then it will increase. If this variance is equals to variance another class, it will increase. But what is the issue? That is the issue. So what you can do, you need to separate. You need to create the separation actually. But here in last example, what we are doing here in P omega 1 and P omega 2 is equal to, we are increasing. This area can increase here actually more. Okay, here also it can increase more. But at the same time, when I'm saying mu, actually mean. So mean is not like that, it is same. For suppose you have 1, 2, 3, 4, 5 values with you, then it may be same. Okay, so but if you have more number of values, then it will not be same. Okay, so okay, I'm here. So suppose this is the class here, one class, this is another class. So my aim here is to reduce this area actually, reduce the error. This is the error actually here. And how it will reduce? It is very easy to reduce actually if there is no overlap actually. Suppose you have separation here and you have a separation. Okay, there is no overlap values, then you can say there is no error, and you can predict very easily. You can predict that the error is at this place. There is no error actually, sorry, there is no error in this one. So if you somehow you can separate it, then you can say that there is no error in this your data. So if the separation is low, the error will increase. Okay, if the separation is large, then error decrease, and vice versa. Okay, so features having like apart mean values, then it is easy to classify. Why I am saying actually, so suppose you have very less values with you, then mean may be almost sometime same. But if you have more number of values, suppose 10, suppose you have more number of values 100, then it is guaranteed actually, and you know that very well, the mean will not be same for any class, because features are same, values are different. Okay, values are different, only number of features are same here. And when you will calculate this sum of uh, values divided by number of variables, then definitely it will be different. So if you can calculate the mean, okay, so you can say that value, it will be separation will be there, mean between mu1 and mu2. When I'm saying that separation is there, at same time I'm saying that you need to increase dimension here. So I'm saying if you have less dimension, 1, 2, 3, 4, 5, chances are there that mean will not be separate. But if you have number of variables like 10, then it will be more separate. Suppose you have 100, then it will be more separate. Suppose you have 1000, then it will be more separate. Separation will be clear. Okay, in between mean actually. So what exactly I'm saying here, I'm saying if we will add more number of features. Okay, more number of features, or features means nothing actually, this is dimension actually. If you are adding the features, definitely you are increasing the dimensions. Okay, so if you will add more number of features or dimensions, it will, yes, what it will do, it will increase the separation. Okay, it will increase the separation, and if it will increase the separation, then prediction will be easy. Okay, so this is one statement here. And second statement at the same time, it will be, if you are from computer science background, you should know about it. Increasing dimensions. Here, if I am increasing the dimensions or the features, both are same thing here, can increase. Yes, anybody can answer what it can do. I'm adding the number of features here, how it will affect. So increasing dimensions can increase the computational overhead. It can increase the computational overhead. Computational overhead. What is the meaning of computational overhead here? Actually, we are using CPU for calculation, or you are using GPU for these calculations. So if I can do any work with 3 dimensions or 5 dimensions, same thing you are doing with 500 dimensions. So definitely it will increase the complexity. Okay, it will increase the complexity. Time complexity will be high in this case. So what we discussed till now, so we have discussed that we have 2 classes with us. Okay, for classifying these classes, we have the options. You can calculate the probability of 2 classes. If the probability is not properly separating the classes, then you can calculate the mean, no variances. If variance is also not working very well, then mean is the best calculation, because it will not be equals to each other. Okay, and why it will not be equals to each other? Because if the dimensions are more or the feature vectors are more in your problem, then definitely mean will not be same at any cost. Okay, so to get this separation for mean, we are adding the number of features in our problem. Okay, so increasing the number of features in your problem, it will create another issue. Actually, the issue is complexity. Okay, so complexity, how it is more actually here. So let me discuss. So the discriminating function here, for when you are using so the discriminating function is, in this case, what will be the discriminating function is, it will be like this. Sorry, 1 divided by n. Okay, and you have k is equal to 1 to n and xk. These are the features actually here, and this is the calculation for mu I. Okay, for any vector, if you want to calculate the mean, so this is the number of features and this is the vector actually xk. So it will give you, the calculation will be like this: x1, x2 until xn and divided by m. So this is the function, we have mu or mean. And here you can see that if you have the dimension is d here, so you are doing calculation for all the vectors, so it is approximately equals to the dimension nd. Okay, so in this case the complexity will be directly dependent to dimension. If somehow the dimension is very large, then this particular calculation will be directly responsible. Okay, and it will increase the complexity. Okay, one calculation which is always required actually when you are doing the classification here. Second calculation which is almost always required when you are using machine learning techniques, that is k is equal to 1 to n x of k. This is the vector here and this is the mean mu I. Okay, x of k minus mu I transpose. So this is the formula of covariance. Covariance matrix you need to calculate always. And here you can check, you have mu, you have dimension, and that is also in square form. Okay. So when you are doing the calculation in matrix, the square is written like this. Okay. So it will give you this form actually, n of d square. N of d square. If you have any doubt, you can ask me why it is n d square. Otherwise, I will skip everything. So it is like n of d square, and the complexity again here it is directly if your dimension is 2, the complexity is 4 in this case. If it is 4, it will be 16. So directly it is increasing here, time complexity. Okay. Second is, the third is, so this is the calculation of covariance, and it is also required always when you are doing any calculation for machine learning. So first calculation is directly dependent on dimension. Second calculation is not only dependent actually, it is a square actually of dimension. So it will be more complex for calculation purpose. Third is, suppose you have number of classes will increase. In this case, we have only 2 classes, but it is you are not bound for 2 classes. So if number of classes are more actually here, are C suppose. So if you have number of classes C, you need to do the calculation for all the classes, and it will be directly the variances you have with you. So it will be, sorry, order of C and D square. It will also increase the complexity. Okay. The time complexity will increase definitely here also. So what is the issue actually here? So I think it is clear now. So we have the two-dimensional, 2-class problem we have here. Only 2 classes are there. Okay, if they are not separate properly, then the area is error. Error will be there in this area. It's an error here. If you want to reduce this error, you need to use means for these classes. Okay, and means should be separate with each other. How the means will be separate? So this graph should be like this. Okay, like this. So mean should be separate. If you want to separate the mean, then you have only one choice. What is the choice here? Dimension you will increase. Okay, dimension, why dimensions are increasing? Dimensions will increase, but why the dimension are increased? Because you are adding more number of features. Okay, when you will add more number of features in your vectors, or then feature vectors, then means will be separate. Okay, means will separate, this problem will solve, and dimension will increase. And what is the issue with dimension? It will increase the time complexity. Okay, and you can't ignore that part. You can't say, okay, I have a lot of machines is there with me, and I'm not worried about the time complexity. So that is not a solution actually, because when we are handling the problems related to machine learning, deep learning, AI, okay, so we are not working with simple machines actually. Okay, so we are taking care about time complexity also. Okay. So what you can do now? Dimensions will increase definitely. So you need to decrease this dimension and with efficient separability. So this is the problem actually for today. What exactly we are discussing here. So we have more number of features with us. Okay. And somehow we need to reduce the dimensions. So what we will do here, so I'm writing one statement. Okay, so reduce the dimension. Feature vectors will be same. Okay, you will take more number of features. Okay, so one more thing I forgot to tell you here. So this case is called the curse of dimensionality. Curse of dimensionality. Why curse of dimensionality? Means increasing the dimensions is very important actually, and you can understand it like, suppose you have 5 images of a cat, only 5 images, or you have 100 images of a cat. So it is very clear that with this statement only, as a layman also you can understand 100 images will make you more efficient, or 1000 images will make you more efficient in comparison of 100 images or 5 images. Okay, so increasing the dimension definitely will separate the classes in an efficient manner. Okay, but when you are increasing the dimensions, that also I have given the proof here. Okay, wait for a minute. Sorry. Hello. Hello. Yes. हाँ 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 बताओ कैसी है नहीं हमको क्षेत्र ही ठीक है लीजिए Okay. Sorry for the problem. Actually, because of Sunday, so many issues are there. So wait for a minute. So, uh, what exactly we are discussing here? So, yes. So increasing the dimension will increase the time complexity. So what we will do here, we will reduce the dimension. We will reduce the dimension. Okay, with some technique we will use here, having efficient separability. Both the thing will be, we will consider at the same time. So what we will do here, the original dimensions we will project like that. The original dimension is d, suppose, and we will project on d dash. Okay, and what will be the meaning here? D dash will be less than or equals to d. It depends on you actually how you can select. So suppose you have 100 dimension in your feature vectors, then you can project on one dimension. You have 1000 direct 10,000 dimensions, you can project in one dimension. So here we are not doing any problem with our original dimensions, will be same, and we will use this principal component analysis to project on, to reduce the dimension actually. Okay, so I think you got the problem for today what we are going to discuss. So here we have two techniques are there. One is PCA, principal component analysis. Already the name we have written here. So this part we will discuss in detail. Okay, but we are not limited actually for this technique only. So we have another technique also. Another technique is also there, that is called MDA. That is called MDA, and this is called multiple discriminant analysis. So we are not going in detail of this technique. Discriminant analysis. Okay. So Okay, so multiple discriminant analysis we will see here. So here actually we are not going in the detail of this one. We will use the variances to separate the classes actually. So suppose this is the one class, this is another class here, okay, and you have mean, this is the mean for this class. So through variances we will try to separate the classes. So what you will do, it will be same mean, you are not doing anything with mean here, okay, and you will try to separate the classes with the help of variances in this case. Okay, so this is our variance here in MDA. This is for MDA. Okay, so this is not for PCA, principal component analysis. So now we will discuss about the PCA, principal component analysis. So if you have used also, today we will discuss the mathematical proof actually for PCA. Okay, so suppose we have n number of features, okay, like this x1, x2, x3 and xn. So these are feature vectors actually. Okay, so these x1 can have 100 images, x2 can have 100, x23 can 100 and xn can 100. So these are the feature vectors actually. Okay, and each having dimension d. So you should be very clear that x1 can have d number of images, x2 can have d number of images, x3 can have d number of features, and this also can have d. Okay, so here in this case I can write like each having dimension d. This is the dimension, d dimension. Okay, so this is very clear actually. We have n number of features and each and every feature is having d dimension. Okay, so this data is also like big data. We have number of images and number of feature dimensions here. So if you want to calculate the mean, so already I told you the formula. So 1 divided by n, k is equal to 1 to n and xk. Okay, so this is the mean actually. So what exactly I will do here? So when I'm saying this d dimension vector I have, so the dimension is d here. So what I will do, I will project this d dimension to 1. Okay, so I will project a d dimension vector to 1 dimension vector. Okay, so the purpose here is to represent the feature vector onto a line. Okay, to present the feature vector onto a line, So this is the purpose actually at this place. So please wait, actually something is not good. Please wait for a minute. हमने अपने पास से लगा दो, मैं देखूंगा आपको। Okay, so we need to project onto a line. So what exactly we are doing here? Suppose I have number of features here. Suppose this is a feature vector, okay, and this is a feature vector here. This is a feature vector here, and this is a feature vector here, okay. And I have here also one feature vector at this place, at this place, at this place. What link is required? I don't know. So if you have any doubt, you can ask me anytime, or you can message also, no issue. Okay, this is one feature vector here. This is one feature vector here. So these are the feature vectors, and what exactly I want to do, suppose somehow I will separate. Okay, so this separation is possible if you have study about SVM, and so many techniques are there. So what they are asking, what our link is required, I don't know. Where is the link? Sir, please share the link. Which link is required? Attendance. I think Geograph sir will send. Okay, so this is the separated, we have separate here, okay, and I have a median here. Suppose I have done the calculation for mean, okay, and this is the direction E. Okay, so this is a like vectors with a line in the direction of E with centroid M. This we have number of vectors here. Okay, number of vectors I have. So this is like vectors with a line. So this line we can draw. Okay, we have the techniques through which we can develop this line, a line in the direction of E, direction of E with centroid M. With centroid M. Okay, so this is the line here we have drawn, and this is centroid M. So what will be the line? Okay, passing through from mean. This line is there. So if I want to write the equation of this line, that will be x is equal to M plus A E. Okay, so this is the line for, this is the equation for this line, which is passing through M. Okay, direction is E, and A is the point available on this one. Okay, so if A is equal to 0, if for this line, if A is equal to 0, then what will be the equation? It will be x is equal to M, And if a is not is equal to 0, in this case a is not is equal to 0, then different point on the line like x of k is equal to m plus a k e. Okay, different point. So suppose you are here in this feature vector, so you can draw a line here like this. So that line will be m plus ake. Suppose this vector is ak here. Okay, this is also another vector ak1 or ak2, whatever you can write. So you can draw a line here, you can draw a line here, anywhere you can draw a line. So this is, so conclusion is that point or a vector xk will represent it on the line with some error. Why I am saying this some error? Actually, suppose this vector is available here at this point, and I want to represent at this point here. Okay, so from this vector to this vector, you are here now, and I want to represent at this line, or I want to project actually. So I want to project on a single line. So this point is here, and I want to project here at this point. I'm here and I want to project at this point. I'm here and I want to project at this point. So this particular vector I will project here. This particular vector I will project here. So this particular vector I will project here, and this one also I will project here. So it doesn't matter how many dimensions are there in your vectors. Somehow you want to project on a single line. Okay, and when you are projecting on a single line, so you can check here, this is the error actually. So this is the error when you are projecting this line. So this is the error. Okay, so every vector is having some error here. What is the meaning of this error and how you can reduce it? So this is the orthogonal line actually I'm drawing here. This is the orthogonal line, this one. Okay, and I'm projecting on this particular line, all this. So what is the error here? This is the error actually. Suppose this is a line here, I will draw this line here, and from here to here, this is the error. Okay, or this is like AK. So what will be this line? M plus A of K E. Okay, this is the equation of this line, and this is the error here, and this line is XK. This is xk. So if I will reduce, I will subtract from this one to this one, so I will go to the error. So what the error is like, so here the error it will be like this: k is equal to 1 to n. Okay, and the vector or equation of vector minus x of k and whole square. Why I'm writing whole square? This is MSE actually, mean square error. So if you have studied a little bit about machine learning or any statistics, so you know the meaning of mean square error. So this is the error here, and the error I will represent with J, A1, A2, AN, and E. This is the error. So these are my vectors here, A1, A2, AN, and error. Okay, or you can write this is the error function. The error function. This is my error function here. Okay, so the above equation I can write in a different way actually. So it is like this: J, A1, A2, AN, E. So I'm just modifying this equation actually. Okay, So the summation will be there as it is. So this a of k I'm writing first here, a of k e minus xk as it is and minus m. So there is no issue in this one. So when it will be inside, it will give minus xk and plus m. Same thing I have done here. So little bit changes I have done in the equation. So this is the error here. Okay, and my purpose is to reduce the error here. Okay, so what exactly we have done? We have number of feature vectors here. Okay, and these feature vectors I have projected on a single line. Okay, and it will convert my dimensions to 1. But when I'm projecting, so I have some error here. So this is the error here. So if I'm at this point, so the equation for this point is this one, and for this one is xk. So if I will reduce, I will subtract from this one to this one. So I will go to this error. Sorry, this error I will go from here to here. So this is the error here, and I got it. How I got it? M plus a of k e minus xk. Okay, but the aim is to reduce the error. And to reduce the error, mean square error, we need the optimization techniques. Okay, so how you can reduce this error? So this is simple mathematics here. So I will open this equation first. A of a square k and e is there. So e is, I will take square plus 2, sorry, minus I, it will be minus here. So minus 2, okay, summation I am taking because I have k number of variables are there, e transpose x of k minus m. So I'm not doing anything extra here, like I'm opening this like a minus b ka whole square. So a square, so this part I have given square here. Okay, minus 2ab, so minus 2a of k e transpose xk minus m, and plus what you will do here, x of k minus m. Oh sorry, this is like in this one whole square. Okay, and this is summation here. So this equation I have opened here. Yes, how you can minimize it? If you know about anything about optimization, you can answer this question. How you can optimize this equation? So how we can optimize? So to minimize the error, find the derivative. Okay, let me write the complete statement, otherwise it will be confusing. So to minimize the error, okay, find the derivative. Okay, it's a part of optimization actually. So I'm not going in that detail. I think you know about it. So derivatives can help you to find the minimum value or maximum value. Okay. So with respect to A in this case. So how it will you can calculate is, so this is the J function you have, and with A you can derivative. Okay, so this is the equation here. So E is a unit vector. Actually, it's a direction here. So we are not considering E. Okay, so this is a square. So what it will give you? It will give you 2 ak. Okay, next is this one. This term is there. 2 of ak e transpose t x k minus m. So ak will convert into 1 and it will give you minus 2 of ak. Sorry, ak will be 1 here. Okay, so ak is not required. So only e transpose x of k minus m, and that will be equals to 0. Only then you can say yes, this is the optimized. A of k is equal to e of transpose x of k minus m. So this is the equation. You will get it from here. Okay, so this is the equation. So E, I'm not considering Y because E is a unit vector. E is a unit vector and that is not required to consider. Okay, unit vector in the direction of line. This is in the direction of line. So what it will give you, mod of E will be 1. So that's why I'm not considering that part. So keep remember this equation, it will help you a lot. Okay, so we have done this calculation. AK is nothing actually, but it is orthogonal projection of xk onto a line, okay, in the direction of passing through mean. So take the orthogonal projection of a vector onto a line passing through the centroid. So here we have done this calculation, no problem. Okay, orthogonal projection you have taken through, it is passing through centroid. So passing through centroid, so which line will be correct? Which line and which direction will be the best? Which direction will be the best? Okay, which line and which direction will be the best? So let me check. So the one calculation already we have done here. So now I will do for the direction. So what I will take here, JE, okay, and that calculation already we have done, a square k. Okay, so because of error you want to calculate, so error is same here and there, both side it will be same, minus 2a of k e transpose x of k minus m, and plus this is I have here x of k minus m whole square. Okay, so J is the unit vector in the direction of line. So JE is nothing actually, it's a unit vector in the direction of line. In the direction of line. Okay, so what I will do here, please take care at this place. A of k, you know very well. What is this? In last I have given the proof xk minus m. Okay, E of transpose xk minus m. So this term here is ak actually. So I will replace actually. So what it will give you, J of E is equal to A of square k E square minus 2 A of k 1 and second A of k I have got from the replacement, and plus this is x of k minus m whole square. Okay, so this is the equation I got here. So E again is a unit vector and that is not required for the calculation. Okay, the mode of E is not required actually, this portion. It will be converted into 1. So what it will give you? So minus 2, this term is like this, minus 2 a square k. So what it will give you? Minus a of k, because this minus 2 square and this is a square k, it is converted to 1, and plus x of k minus m whole square. Okay, correct? So this calculation is okay here. So now what I will do, this a of k I will replace with this equation. So what it will give you? Minus okay, this is okay, yes, minus E of transpose. Sorry, this is square actually. This is square here. Okay, because A square k. E transpose x of k minus m whole square plus x of k minus m whole square. Okay, and this term can be written like this. E of transpose will be outside. Okay, and it will give you x of k minus m, and then x of k minus m transpose and E plus x of k minus m whole square. What is the meaning? So the meaning here is, suppose you have E square. Okay, you want to calculate E1 square plus E2 square plus E3 square. So you can write like this: E1, E2, E3, and transpose of this one: E1, E2, E3 in matrix form. Okay, so suppose you have mean square error of like E1 square plus E2 square plus E3 square, and you have matrix for all this. So you can convert E1, E2, and E3, and then transpose of this one: E1, E2, and E3. So if you will do the calculation for this one, so it will give you E1 square plus E2 square plus E3 square. Same thing I have done here. So I have the square of this one. So to do this calculation, I took xk minus m and transpose of xk minus m. So it will give me like this form. So there is no error in this one. So I have done this calculation here. And what it will do? So I will write this equation again here so that it will be easy to understand. So this, what I got from the last, this is my equation: J of E is equal to minus E transpose x of k minus m, okay, x of k minus m transpose E plus x of k minus m whole square. So this is the equation I got it. And already when I started this lecture, that time I told you the covariance matrix, and what was the formula here is like 1 divided by n sum You will start from k is equal to 1 to n. Okay, x of k minus m and x of k minus m transpose. This I told you in starting. So here I don't have this 1 divided by n portion here, but remaining it is almost same. If I will leave this part and I will leave this part, so this is almost same like covariance matrix formula. Okay, so I know this is not the covariance, so this is, I will replace this with another value that is called S, and it is called a scatter matrix. Scatter matrix here. So what it will give you now, the equation will be JE is equal to minus E transpose SE, okay, plus x of k minus m whole square. Okay, so this is the equation. Now, if I want to reduce this error, okay, so it is very clear if this value will maximize, because it's a negative value here. If this value will maximize, then JE will minimize. JE will minimize. Okay, and this is the optimization here. Same thing is required. Somehow I need to reduce the error here, and I got it. So somehow if you can increase this value, then you will decrease the, you can minimize the J. Okay, so here I will use the mathematician equation that is called Lagrangian equation. Actually, Lagrangian formula is there. So mu is equal to E transpose S E minus lambda E transpose E minus 1. Okay, and if you will take the derivative of this equation to minimize on over with respect to E, so because it is like E transpose E, already I told you it is like E square. So what it will give you, 2 S E. Here also E transpose E again will give you E square. So it will give you 2 lambda E, and this term will be 0. Okay, and is equals to 0. So what it will give you, SE is equal to lambda E from here. SE is equal to lambda E. So the last equation I got here, JE is equal to S is equal to lambda E. JE will be like E minus E and lambda E and plus x of k minus m whole square. And here his purpose is to maximize this one. You need to maximize it. Okay. So in this case, when I am discussing, E is an eigenvector here. Okay. Of S, and lambda is eigenvalue. Here also lambda is eigenvalue. So now it is very clear from here, okay, to maximize E lambda E. So it is very clear from here that to maximize E lambda E, what is the requirement? we need to increase the value of lambda. We need to increase the value of lambda. Value of lambda here. Okay. So if we will consider only one maximum lambda value, an n-dimensional vector will be one-dimensional. Okay, so please check. So this is the PPT actually, whatever I have told you. So already we have discussed this part in detail. Okay. So everything we have discussed, this part also. So just you read this line here actually. So I have written, so if we consider only one dimension lambda value, one maximum, then n-dimensional vector will be one dimensional. If you will consider multiple eigenvalues, okay, so if one maximum value you will choose of lambda, one maximum value of lambda, okay, then it will be converted into one dimensional. If you will choose more number of variables, then it will be converted into d dash, and that you matters with you, it will be less than or is equal to or not. Okay, this is all about the PCA actually. Okay, so I will take one example, a numerical example, and then it will be more clear actually. So please wait for 5 minutes. Okay, I will take another. So I will take one numerical example so that you can understand it actually. So what I will do here, so same thing actually. So I will take some data here. Okay, then step 2, what I will do here, I will compute the mean vector. Mean vector that is always required. Okay, then I will calculate, I will do the subtraction here. Subtraction is required for calculation of mean or the variance actually, because in my variance you have seen xk minus m is there. So I will subtract mean from the data. Okay, from data, given data. So it will give you xk minus m. Then step 3, 4, sorry, and it will, here I will calculate the covariance matrix. I will calculate the covariance matrix. Okay, and then step 5. Okay. Step 5 is like calculate the eigenvectors and eigenvalues, because that is required for PCA. I will calculate the eigenvectors and eigenvalues. Okay, and step 6. Okay, I will choose the components to form a feature vector. Okay, for feature vector. And step 7, I will driving the new data set from the existing one. Okay, so here already I told you why the maximum value of eigenvector is considered. Okay, so I will take the data here, x is equal to 1, 2, 3, and I will take another y is equal to 1, 5, and 3. So this is for class 1. This data set is for class 1. Okay, I will take x is equal to 5, 6, 7, and y is equal to 6, 7, 8, and this is for class 2. I have 2 classes here. So this is the data already you have. Okay, now it will be converted to feature vectors automatically by your Python language. So how it will be visible to you? It will be visible like this: x1 is equal to, sorry, I have done some mistake. This is 2 actually. 2, 3, 4, this vector, sorry. So this is 2, 3, 4. Okay. So it will be 2, 1, x1. Okay. So this value I took from here and from here. x2 will be 3, 5. Okay. x3 will be 4, 3. Okay, then x4 will be 5, 6. X5 will be 6, 7. X6 is equal to 7, 8. Okay, so like that it will be formed. So N is for 6 here and D is 2 here in this case. Or in matrix form, if you want, you can represent. So it will be 2, 1. Okay, 3, 5 and 4, 3 and 5, 6 and 6, 7 and 7, 8. Okay, so this is the forming matrix form we have formed. Okay, so next step 2 is, what is the step 2 here? Calculate the mean. So calculate the mean. Okay, so it is very easy to calculate. So what we will do, 2 plus 3 plus 4 plus 5 plus 6 plus 7 and divided by 6. Okay, and second, for second class, 1 plus 5 plus 3 plus 6 plus 7 plus 8 and divided by 6. So what it will give you, 2 plus 3, 5, 9, 14, 27 by 6. Okay, and it will give you 4.5 almost. Okay, and 6 plus 3, 9 and 6, 15 and 7, 30. Okay, 5. So this is the mean vector here I got. Okay, so mean vector is like this. You will got 4.5 and 5. Okay, now step 3 is also very easy to do. The calculations we need to do actually here. So what it will give you, x1 is equal to, so already I told you it will be xk minus mu. Okay, in this case, and xk is what is the value of your original vector in starting, that is 2, 1. Xk is 2, 1. So what it will give you, 2 minus 4.5 and 1 minus 4.5. Okay, 2, 1. 2, 1 from here. This is 1 and this is 2. And it will give you, sorry, I'll write here, minus 2.5 and minus 4. Sorry, this is 5 actually. This is not 4.5 here, this is 5. This is 5. So minus 4. Okay. Similarly, x2. What will be x2? The 3 minus 4.5 and 5 minus 4.5. Sorry, 5 minus 5. So it will give you minus 1.5 and 0. X3 will be 4 minus 4.5 and 3 minus 5. So it will be minus 1, so sorry, 0.5 minus minus 0.5. Okay, and minus 2. X4 will be 5 minus 4.5 and 6 minus 5. So it will be 0.5 and 1 minus 1. Now 6 minus 5 plus 1. Okay. X5 will be 6 minus 4.5 and 7 minus 5. So it will give you 1.5 and 2. And x6 will be 7 minus 4.5 and 8 minus 5. So it will be 2.5 and 3. So like that you will go to the factors. So if you want to write after this calculation, so you have minus 2.5 minus 4. Second vector you have minus 1.5 and 0. Next you have minus 0.5 and minus 2 and 0.5 and 1, and you have 1.5 and 2, and you have 2.5 and 3. Okay, so this calculation we have done. So we have done this calculation. Now I will calculate the covariance matrix as a next step here. Covariance matrix I will calculate, and what is it will be m1 is equal to what it will give you x1 minus mu and x1 minus mu the transpose. Okay, so divided by n I will do after some time, so because it is not required at the same time, so it will give you minus 2.5 and minus 4. Okay, the transpose. So what will it will give you 6.25 and 10, 10 and 16. Okay, m2. Next equation you can calculate. So I can write directly here now, minus 1.5, 0. Okay, and minus 1.5 and 0. And it will be 2.25, 0, 0, 0. Okay, m3 you can calculate here, minus 0.5 and minus 2. Okay, minus 0.5 and minus 2. Okay, and if you will do this calculation, so you can say 0.25, 1 and 1 and 4. Similarly, m4 I can calculate m4 here, so it will be 0.5 and 1 and 0.5, 1. Okay, so it will be 0.25, 0.5, 0.5, 1. Okay, m5 will be 1.5, 2. Okay, 1.5 and 2. So it will also give you 2.25, 3, 3, 4. Okay, similarly m6 I will calculate here. So it will be 2.5 and 3, and here 2.5 and 3. So it will be 6.25, 7.5, 7.5 and 9. So covariance matrix, I have calculated. This is one calculation we have done for covariance. For second, we need to divide by n. So what I will do here, I will take this value. Okay, all the matrix you will add with this, all the matrix you will add, and then you can divide it. So what will be the covariance matrix here? That will be 1 by 6 and total sum. Okay, like M1 plus M2 plus M3 plus M4 plus M5 plus M6. Okay, so what it will give you, the total values are like 17.5 and 22 and 22 and 34. So we have done the sum actually for last calculation we have done. So the covariance matrix will be 2.92, 3.67, okay, 3.67 and 5.67. So this is my covariance matrix. I got it here. Okay, so now step 5. So what you will do, we will calculate the lambda is eigenvalue. Okay, so there is a equation m minus lambda I should be equals to 0. I is identity matrix here. So m is covariance matrix in this case. So here I will calculate the lambda. Okay. So the covariance matrix already it is written there. So it is 2.92, 3.67, 3.67 and 5.67. Okay, and here it is lambda 0, 0, lambda is equal to 0. Okay, and you can do this calculation. 2.92 lambda, 3.67, 3.67 and 5.67 lambda. Okay, is equal to 0. And more calculation if you will do here, so it will give you 16. Sorry, this is not the case here. No, this is not correct. So you can write the 2.92 minus lambda from the last equation, 5.67 minus lambda minus 3.67 into 3.67 is equal to 0. And if you will do this calculation, you need to multiply, okay, 5.67 into 2 by, and it will give you 16.56 minus 2.92 lambda, okay, minus 5.67 lambda plus it will give lambda square minus 13.47 is equal to 0. Okay, and from here if you do lambda square minus 8.59 from here lambda, okay, and it will give you plus 3.09 is equal to 0. And if you want to solve this equation, you can solve it, and when you will solve it, it will give you two values of lambda. One will be 8.22 and lambda 2 will be 0.38. So when you are getting two values of eigenvalue, so you will take the maximum value always. Okay, and that is the fundamental concept of PCA actually. Maximum value we choose. Why we choose maximum? Already the proof I have given to you. Okay, why we are selecting the maximum value. So clearly the second value is very small and we are not going to consider. Okay. So let me find the eigenvector. Okay. So we need to find the eigenvector. You have two values. One is 8.22, one is 0.3. What is this value? 0.38. So find the eigenvector. Okay, corresponding to eigenvalue lambda 1. Okay, so this is mx is equal to lambda of x. This is the equation in our simple mathematics, where m is a covariance matrix, x is the eigenvector here, which you need to calculate. Lambda is the eigenvalue. Already you have calculated this value. So it will give you 2.92, 3.67, okay, 3.67, 5.67, okay, and it is x1, x2, and already you know this, it is 8.22, and here x1, x2. Okay, so through this you will get the value of x1 and x2. So if you will do this calculation, you will get so many equations will be there. 2.92 x1 plus 3.67 x2 is equal to 8.22 x1. Okay, and from second you will get 3.67 x1 and plus 5.67 x2, and it will also give you 8.22 x2. Okay, so on simplification, you can simplify these equations and it will give you the 5.3 x1 is equal to 3.67 x2 and 3.67 x1 is equal to 2.55 x2. Okay, so eigenvector from here, it is very clear. So you can do this calculation. And my eigenvector is x1, x2 is equal to 2.55 and 3.67. So this is the principal component for given data set. So this is the principal component. So with the help of this, you can calculate the projection of any vector. Okay. So suppose I want to calculate for first vector. So, okay, the first vector using PCA. So use PCA to transform to 1, okay, onto eigenvector, onto the eigenvector. So the formula here is actually how you can, so this is, you can take transpose of eigenvector, you can take into feature vector minus mean vector So you have 2 transpose of eigenvector will be 2.55 3.67 into already this calculation you have done 2.5 minus 4. So when you will do this calculation, it will give you minus 21.055. So what it is giving the 21, this the projected value of it will be minus 21.055 using particle component, this principal component analysis. Okay, so this is the calculation we have done here. Okay, so already we have discussed all the thing in detail. These are the references here. So if you have any doubt, you can ask me. So I have the Python programming how you can do for principal component analysis. So I have this I took this for plotting the graphs, this library, matplotlib, numpy for some mathematical calculation, pandas for our data set. Okay, sklearn.data set is there. Okay, from I'm directly importing this data set. Load breast cancer. Sorry, I need to connect. So it is connecting. So yes, so I have taken the data, load breast cancer. Okay. I got this data, and here I'm printing the description of this data and keys. Okay, so everything is there where everything it is given, radius, texture, so all the details of data set is here. Okay, so now we have got it. Now I will use data frame, okay, for this data set. So everything is all the details, mean texture, mean parameter, mean area, mean smoothness. And because I'm printing head here, so it will give me 5 first rows for the data. Okay, you can print entire values also. From here, I'm standardizing my data. So sklearn, pre-processing, import, okay. So that is scaled the data. So here I'm using this PCA actually. So I'm using from sklearn.decomposition import PCA. Okay, already it is available in Python. So PCA is equal to this components to 3. I have written here. So one more thing I want to tell you here actually. So the data set is saying the 569 and 30 numeric values. So number of instances 569, number of attributes 30 here. Okay. So now I'm coming here back. So this is okay. They scaled the data here PCA. So this is the available algorithm or the available technology is there. PCA.fit scaled data already you have taken, transform it, and I will compile it. So now you can check that this it was 569 into 30. This is the original data actually, and I have converted into 569 into 3. So if I'm taking the more than one value of eigenvalues, then it will give to that one times. See again, so this 30 is converted to 1 here again also. Okay, so if you want to convert to 10, you can convert to 10 also. Because why it is actually working like this? Because because of this statement I have written here. So if I will consider only one maximum lambda value, n dimensional vector will be one dimensional. Okay, if multiple, then less than this one. Okay, so here I have drawn this actually for first principal component. This is the classification we have done through this. So this is all about the principal component analysis. If you have any doubt, you can ask me.
Anybody? Ananya?
Yes, sir. Good afternoon, everyone. So, as we come to the end of today's session, I would like to take a moment to thank Sushil sir for his expert guidance throughout the session. Your insights have been incredibly valuable for our understanding of AI, and we are grateful for the time and efforts you have dedicated to our learning, sir. And thank you all for your active participation today. I think no one has any doubt. I encourage you all to go through the class recording to strengthen your concepts, and I look forward to seeing you all in the next session. Once again, thank you so much, sir.
Thank you
Greatly
very much.
appreciate your expertise on AI. Have a good day, all.
Thank you very much, madam. Thank you very much for inviting me here. So thank you very much, all the participants, for listening me. Okay.
Okay. Thank you, sir.